আমাকে একটু কেউ বলে দেবে যে শেষ আমরা কোথায় ছিলাম, কোন জায়গায়? অভিষেক, আগের দিনে অনেক ইন্টারাকশন হয়েছিল, কোথায় মনে আছে কোন জায়গাটা?
সেই পিডিএফটা শুরুর দিকেই বোধহয় ফার্স্ট
শুরু,
2-3টে পেজ হয়েছিল।
না না, শুরুর দিকে মানে কোন জায়গাটা থেমেছিলাম, মানে কোন
এটা
ডিসকাশনে?
হয়ে গেছে, এটা হয়ে গেছে, স্ক্রল করুন বলছি।
হুম
এগুলো হয়ে গেছে,
হুম
এই আর্টিকেলটা হয়ে গেছিল।
হুম, এগুলো হয়ে গেছে।
না না না, এইগুলো হয়নি, ওই
এগুলো,
আর্টিকেলটা হতে হতে থেমে গেছিল।
এইখানে হতে হতে থেমে গেছে না?
হ্যাঁ,
আচ্ছা আচ্ছা, ঠিক আছে, আমি জাস্ট হালকা করে একবার বলে দিই এখান থেকে। হ্যাঁ, যেটা হচ্ছে আমি যেটা বলেছিলাম সেটা হচ্ছে যে ক্যানোনিক্যাল এনসাম্বল। হ্যাঁ, ক্যানোনিক্যাল এনসাম্বল নিয়ে কথা বলছিলাম, এবং সেখানে কি প্রবাবিলিটি, মানে যেহেতু প্রচুর মাইক্রোস্টেট আছে, সেই স্টেটগুলো অ্যাক্সেসিবল প্রবাবিলিটি কি? হ্যাঁ, তো সেইটা আমরা বোধহয় জানতে চাইছিলাম, প্রবাবিলিটি অফ ফাইন্ডিং দ্য সিস্টেম ইন এনার্জি ইআর। তো এখানে যেটা হচ্ছে ক্যানোনিক্যালে ডিফারেন্স হচ্ছে এখানে ইউ ইউ ডিফাইন দ্য ম্যাক্রোস্টেট বাই n, v and t. You keep the temperature at equilibrium temperature, constant temperature, and the energy may vary from 0 to infinity in principle, but probably it will not vary that much, but in principle it is allowed to vary from 0 to infinity, and to maintain the temperature, constant temperature T. Okay, so this is the canonical ensemble, that is what is different from the micro canonical ensemble. And here actually we wanted to figure out the probability of finding the system in the energy value ER. Okay, so what is the probability that the system could be found with the energy ER? There are two possible ways of finding the probability distribution. One is regard the system as in equilibrium with a heat reservoir at constant temperature and study the statistics of energy exchange between the two, and that we were doing actually. And yet another method is regard the system as a member of the ensemble. Member of the ensemble means you have number of replicas of the system, and one of them is treated as a system and others are kind of members of the ensemble. And then you distribute the energy, total energy E, among the members of the ensemble, and then you try to figure out the statistics of sharing the process, and from there you can eventually extract the probability of finding the system with certain energy E. Okay, there are two procedures. I was adopting the first procedure first. So this is the equilibrium of a system with a heat reservoir. This is the system, it is in the reservoir R, and the total energy of the system is conserved, that is ER prime plus ER equals to E naught. That is what I named earlier. E naught is total energy, and the system is having the energy ER, and of course temperature is maintained at T. And then we were asked what is the probability that the system will be having the energy ER. That was the question that we asked. Now then, you see, since R prime is the energy of the reservoir, it has to be naturally much bigger, much larger than the cis energy of the system, right? And therefore, ER is much less than ER prime, and therefore the ratio is much less than 1. Obviously, these things are needed later, and hence obviously E naught, because E0 is even larger than ER prime, and therefore ER by E0 total energy is of course certainly less than 1. Now the system that one specified, the reservoir R can still be in any one of large number of states which are compatible with the energy values ER. I was saying that the system, in fact the reservoir total energy is not, the reservoir can be in any of many possible microstates, and let's say that number of microstates is this omega ER prime. Okay, more and more the number of microstates of the microstates available for the reservoir, then more and more the probability that the reservoir would be found with the energy ER prime, and hence the probability that could be found the system with energy none other than the ER, because ER plus ER prime is total energy E naught. So if the reservoir is found with the energy ER prime, then it has to be that the system should be found with the energy ER, right? So the probability is directly proportional to this number of available, more and more available microstates, and more the probability that the reservoir could be found with this energy, and hence more and more the probability that the system could be found with energy ER. Okay, so that was the basically logic, and that I explained. I spent lots of time to explain that in the last class, as I remember. Now that is what I'm saying. The probability is directly proportional to the number of microstats. So PR is the probability that the reservoir could be found with energy ER prime, and hence the system could be found with energy ER, and that is proportional to this. And also you know that microstates and the entropy are connected by this formula, S equals to K ln omega, and therefore ln omega is S by KB, and therefore you can write omega in terms of the entropy, and hence PR is proportional to this. This you can write as this could be written in terms of this. You can write that PR is proportional to omega. ER prime is nothing but E naught minus ER, and therefore and similarly, if you ask what is the probability that the system could be found with energy ES, then that probability is PS is proportional to omega of E naught minus ES, similar to this one. Okay, that is what I've said, that PR is a probability that the system A is found with energy ER, and PS is a probability that the system A is found with energy ES. Okay, so then basically this is proportional to this is proportional to this, that you can rewrite again, that PR is proportional to this, PS is proportional. Now taking the ratio, PR by PS is nothing but omega a function of E0 minus ER by omega function of E0 minus ES, and that is what you can write in terms of entropy. Then you have to write it exponential of S entropy function of E0 minus ER by KB, and for this it is exponential of S by K, S function of E0 minus ES. Okay, so this you can write a single exponential in this form, 1 by KB, S of E0 minus ER minus S function of E0 minus ES. Okay. So you can rewrite this again like this, and then you expand this. You see E0, the total energy, you expand about this, and this is pretty small about this, and hence you can expand. It's like x plus delta x. So you expand this about E0, then it is E of S of E0, there is del E and V, then the change is minus ER as you do the Taylor expansion. So this is yet another expansion for this about E0, and then you get, and this expression from thermodynamics, you know, this is nothing but probably 1 by T, and therefore you can write 1 by T here, and your expression then from there, this and this gets cancelled. Basically you are left with this, and this is 1 by T, this is 1 by T. And somebody has popped up, and therefore so Acha, do you have this note with you? Did I send it to? Did I send this note?
না স্যার এইটা পাঠাননি
পাঠাইনি
না স্যার এটা পাঠান
Oh, okay. So should I send it now, or I will send it after the class?
as you wish.
Okay, then I'm class for you. Okay, so this is your this one, and it is totally from Pathia. You can even follow the Pathia also. So PR by PS is this. So if you substitute this, then it is exponential minus ER by KBT plus exponential. So you can write at the ratio form, it will be minus ER by KBT by e to the minus ER, and therefore P is proportional to e to the minus E by KBT, right? And therefore PR is proportional to, you can see from this that PR is proportional to EPR minus ER by KBT. And is proportionality constant, you can have the proportionality constant and then equate them. And then of course, you know, the total probability has to be 1. If you sum over R, it can have with any energy state, and if you sum over R, PR, that should be 1, and therefore if you have the proportionality constant here as P naught, then PR equals to P naught is minus ER by KBT, and therefore sum over R, you get P naught, sum over this is 1, and hence P naught is 1 by sum over R, all possible states, it is minus CR by KBT. And if you substitute it here PR, then PR comes out to be it is minus CR by KBT by sum of R minus CR by KBT. So this is what is the probability that the system could be found with an energy ER. Okay, this is the probability. Okay, and this term is the denominator, that sum over all possible states, it is a minus PR Rh state by KBT. So this one is known as partition function. Okay, in statistical mechanics, you know that whenever you want to calculate any quantity, then you try to link it with the partition function. Because in statistical mechanics, you have the partition function, and then that can be linked to, that can be used to calculate many, measurable quantities through the connection between statistics and thermodynamics. So this is the partition function. Just look at it and remember it. Don't forget it. This is the partition function. Sum over all states, e to the minus ER. This is the state energy by KBT. Or many times you write e to the minus beta ER. Beta is 1 by KBT. E to the power minus beta ER. Sum over R. R is all possible states. I repeat, all possible, sum over all possible states. That is the partition function. Partition function plays a key role in statistical mechanics. Okay, so this is the probability. This is what we obtain. We ask the question, what is the probability that the system could be found with energy state from ER? So this is the probability we have found, and the denominator is the whole thing. It's called the partition function, and this partition function, can be linked to free energies, and from free energies, you can use the statistical relations, thermodynamical relations, and you can calculate many physical quantities of your influence. Okay, so this plays a very key role in statistical mechanics. Now, second is, as I said earlier, if you recall, there are two approaches. The first approach, that is the system is in equilibrium with the reservoir, and the second approach that we said regard the system as a member of the ensemble NVT, member of the ensemble corresponding to the macro state of the system NVT, in which the total energy E is distributed among the members of the ensemble, and then study the statistics of sharing the process. From there, you can calculate again the probability of finding the system at some energy, say ER. Okay, some energy E. So that is what we are going to do. A system in canonical ensemble. Treat the system as a member in the ensemble and the energy E shared among the members of the ensemble. This is T is missing, THE. Among the members of the ensemble, and study the statistics of sharing the energy among the members. That's the whole key point in this approach. This is a statistical approach, ensemble approach. We consider an ensemble of eta identical systems. Okay, in the ensemble you have eta members. Okay, identical systems which are certainly labeled as 1, 2 up to eta, and total energy that is shared among the members of the ensemble is this E, this curly E. Now let that ERs are the energy eigenvalues of the systems, possible energy values associated with the system of ensemble. What I mean by this? It means that ER, suppose there are some members having energy, say ER, there are some members which are having energy ES, there are some members which are having energy something different, and so on. That is what I mean here. Okay, so energy is distributed. So let ERs are the energy eigenvalues of the system. Okay, and now R is the index associated to distinguish different energies. Okay, now that means that let's in our systems are having the energy ER. Okay, let that you have total eta, this number of members in the ensemble, or this number of similar systems you have, and among these, so let's say inner systems have the energy ER. That means it simply means, it is a general notation. It means N1 systems are having energy E1, N2 systems are having energy E2, N3 systems are having energy E3, and so on, such that the total number of systems is conserved, that is eta, and therefore sum over NR equals to eta, total number of systems. And also, if there are inner systems having energy ER, then these inner systems will have total energy NR, the product of NR and ER. And then if sum over all R, then you get the total energy that is distributed over the members of the system. And that should be equals to eta times the average energy of each system, each member in the ensemble. Okay, in the ensemble, these systems are having different energies, but on the average, each member of the ensemble is having an energy U, total energy U. Okay, so a system having an average total energy is U. That's why eta times U is the total energy E, which is nothing but sum over NR ER. Okay, so basically N1 E1 plus N2 E2 plus N3 E3 and so on. Okay, such that sum over N1 plus N2 plus N3 dot that becomes the total number of systems. Okay. So this has to be maintained. Okay. Now on the average, each member of the ensemble has energy U. That is what we said here, average energy. Okay. Now, given that any set NR, because you can have different kinds of sets, right? You can have N1 with E1, N2 with E2, N3 with E3. So that is one set, N1, N2, N3, N4, and so on. And you can have yet another set where N1 prime, number of systems have energy, each having energy, say epsilon 1 prime. Then N2 prime systems have energy E2 prime. Then N3 prime number of systems will have energy E3 prime, such that sum over NR prime equals to eta, total number of systems, and sum over NR prime ER prime, that should be equals to total energy curly E, right? So NR prime could be another set such that sum over R NR prime equals to eta, sum over NR prime ER prime should be equals to total energy. So there are different kinds of sets, provided that they do satisfy this and this. Okay, as long as these two are satisfied, I mean with the what should I say, with the how do I say that preserving these conditions, you can have different sets of NR, right? So these sets are possible and they represent a possible mode of distribution of total energy E among the eta members of the ensemble. Okay. Now further, So Abhishek, up to this, is it clear?
Yes, sir.
Okay. Now, Moshumi?
Yes, sir.
Okay. Now, furthermore, any such mode can be realized. Any such mode, these are, I'd say, these are kind of a mode, okay? Any such mode can be realized in a number of ways because we may affect a reshuffle among these members of ensembles whose energies are different and thereby obtain a state of the ensemble which is different from the original one. What I mean is that we can reshuffle the members having different energies, not within the same energy. Say N1, suppose N1 systems have energy, each are having energy E1. Then it says that shuffling among themselves doesn't matter, doesn't make any change. But if the systems have different energies, then we can shuffle them, okay, and then we can have yet another distribution, okay. So that is what it is saying, that any such mode can be realized in a number of ways because we may effect a reshuffle among these members of the ensemble whose energies are different and thereby obtain a state of the ensemble which is different from the original one. Okay, so this is the statement. What I meant is that you have the cluster of systems having different energies, then you can reshuffle among the clusters, between the clusters, having different energies, and you can get different configuration, and hence that could lead to yet another kind of mode which is different from the original one. Now, the number of ways we can achieve that configuration, the configuration in consistent way, of course, as I said, it has to be maintained because this is conserved number of systems, the total energy is conserved. So we have to achieve those configurations with the by maintaining these conditions, and that should be equals to, you can shuffle all the members, you can have the permutation among all the members, and of course divide by the permutations among the members having the same energy, that is eta factorial by n1 factorial, n2 factorial, n3 factorial up to n factorial. This is for a particular set nr, okay, nr for a particular set nr where n1 systems are having energy e1, n2 systems are having energy e2, and nr systems having energy er. For that particular set of configurations or that particular set, you can have so many possible configurations and hence so many possible modes, and you can say so many possible maybe micro steps. Now this is for the set nr, as I said. Now again, you see, for a distribution set, so you can have different sets, different kinds of distribution set, right? Again, for a distribution set nr, all the states satisfying the conservation number and energy are equally probable, and hence the frequency of occurrence of nr is directly proportional to wnr. Now, for a certain configuration, as we said, that all states are equally probable, and therefore the frequency of occurrence of this set is directly proportional to W of nr. Okay, so this is the number of ways, the number of microstates available, and since all states are equally probable, and therefore this set, occurrence of this set, is proportional to, as we said there, the probability of occurrence with energy E is proportional to the available microstates in the reservoir or with energy Er prime, right? Similarly, here also, this is the, for this set, this is the number of ways, possible configurations or possible modes or possible microstates available here. Okay, and the occurrence of this set is of course certainly proportional to the number of configurations. The number of configurations more, then the probability of occurring this set is more. Okay, that's the logic. Now, the most probable mode of distribution is one for which W is maximum. So you have many possible sets, right? This is one distribution set. You can have nr prime, curly bracket nr prime another. You can have another, yet another one, curly bracket nr double prime, and so on. You can have many possible, sets, right? Now, you can have many possible sets. Now, the point is that there could be a set for which this number is maximum. Okay, the most probable mode of distribution is one for which W is maximum, and we denote the corresponding distribution set as nr star. Okay, now at this point I would like to I would like you to recall the random walk problem, the distribution in random walk, and there, do you recall that the most probable value was the average value? Do you remember that? Most probable value was the average value in case of a random walk distribution?
Yes, sir.
Yes. So same thing will happen. This is no different. The same thing will happen here also. The most probable value is the average value. Okay. It may be seen that W nr star, this is the most probable set for which W is maximum, is so large compared to the other WNR that the effective contribution to any physical quantity comes from mainly from WNR star. In fact, we may recall the random walk problem where we proved that the most probable value is the average value. The same holds here, and hence NR average is nothing but the NR star. What is the NR average? NR average is, you sum over all possible sets, then NR WNR by sum over all possible sets WNR. Okay, so this is the average, and that if you do a rigorous calculation, you can follow that here. You can do rigorous calculation if you wish to. Then you will find that this is nothing but NR star. Okay, so most probable value is the average value of NR. Okay, now this NR average, so this is the average value, NR average by eta. So NR on the average, this NR on the average, this NR number of members of the ensemble are having energy ER, okay, on the average, and that value is nothing but NR star, and therefore NR average by eta equals to NR star by eta, and this is nothing but the probability, is the total number of systems we have. Among that, this is the average number of systems having the energy ER, and therefore the probability that the system will be having the energy ER is nothing but average NR by eta or NR star by eta, because these and these are same. Okay, as I said, you may go through the rigorous proof. However, we have seen earlier that in the random walk problem that the most average distribution value turns out to be the most probable value. That is because the most of the contribution that comes from the most probable value, and that's why the average value and that becomes equal. This is the probability of finding the system, probability of finding the system with the energy ER. Now, let us pay attention to the most probable set. Now, let us look at this. Now, NR star, this is the most probable set, okay, for which W is maximum, right? So then W NR is this, and of course you have to satisfy this and take the log. When the large number, take the log. It's a kind of convention to take the log of this, and then you use the Stirling approximation and eventually you write this in this form. This is in this form, of course, with the, because these are the constraints you have, these are the conditions you have, and therefore from there, if you take the delta on both sides, delta nr sum over r should be 0, and er delta nr also should be 0 from this condition. These are the constants you have. So this is the value of this this distribution, I mean this number of possible configurations for the set nr, and this you have taken the ln of this, and this is this, and you have to maintain these conditions. This is the constant. Then you can find the maximum value. Then you take the variation of this. You take the variation of this. Would be, you can do it by yourself. I have done also by myself. So you can take the variation, and eventually will obtain this is this equation. Then this equation 1 tells us about the variation of ln w, which will be 0, along with the constants that I said. Constant is this, and of course total energy is constant. So this corresponds to this, and this corresponds to this. So you have to take these constants into account. That means you have to have the Lagrange multiplier. I think you have come across Lagrange multiplier, right? If you want to find some, maximum value with some constants, then you bring in the Lagrange's multiplier. Do you know these things?
Yes, sir.
Yes, sir.
So okay, bring the Lagrange multiplier, say alpha with delta n and beta with this, and therefore eventually you will have this total should be 0, because here you have this should be 0, this should be 0. Along with that, you have to add these things. Then eventually Lagrange multiplier makes sure the constants are taken into account along with this, and therefore you take this equation A from here, this and this equals to 0, and therefore from this you get eventually you can go through these steps and nr star, because you have taken the variation and made it 0 with the constants, and therefore this is the most probable set, right? nr, and ln nr, and nr turns out to be, nr star turns out to be c e to the minus beta er. And then if you sum over nr all of this eta, and that is say sum over this, and from this you get c is eta by this, and if you put it back there, nr star is eta this by this, and therefore nr star by eta equals to this value. This is again, since nr star is nothing but the expectation value of eta r, and therefore this is again the PR. Okay, the probability that the system could be found with energy ER. This should be R. Okay, this is, it looks like N, but this is actually R, and this is the partition function. Now average energy per member of the ensemble is the U equals to this curly E by eta, and of course this E is nothing but a star ER by eta, and therefore you can have that this one is nothing but PR. So basically you can have PR here. So ER sum over R, ER to the minus ER. This is a simple average value, the standard average value. So this is the average value of the energy. Now the physical significance of various statistical quantities, how do you link them with this? Now PR is, as I said, I'm repeating this again, and then U is this, as I said earlier, U is this, and that you can write it in the form minus del del beta. This is a kind of tricky way of writing minus del del beta of ln of this. This is the kind of partition function. You see, the partition function is related, so you can use the partition function to calculate the total energy, total average energy of the system. Again, you can write PR. This is the form you can write in a tricky way, minus 1 by del del. This is very often, this tricky way of writing is very often, you come across very often of this tricky way of writing in statistical mechanics. Minus del del beta of del of ER ln of this. If you do this, you will get this. And so this is the one way of writing this one. Then now let us define A. Okay, A is this. Let us define this, and eventually we'll find A is nothing but the Helmholtz-Wave energy. You see, I'm just telling you all the steps are not available in your Papria, so you can just follow it, and I'll give you the note, and therefore you can just keep your Papria by side, and you can go through this note, and then many things are not written here. You can just follow the Papria, the kind of explanation that they have given in Papria. So you should follow that, and also you can get intermediate steps from here. So let us define a quantity A. All I want to say that if you know the partition function, you can use that, and you can get to calculate, all possible physical quantities of your interest. So A is this, then beta you multiply is this, minus take there is this, then differentiate. D of this is nothing but, you see, this one has beta and ER, so del beta. Then this, as you do del beta of this, the beta plus del ER, and then of this DER, and R, there are many R's, then sum over R. So you get this from there. This one equals to, what is this? U. What is U? What is U? U is this. Okay, I'm keeping this here. Okay, I'm keeping this here, or rather do I? Let me send you the note. Then you're able to do the calculation there yourself. আমি তোমাকে পাঠাচ্ছি এটা। Yeah, send a copy. WhatsApp. দেখো তো চলে গেছে, পেয়েছো কিনা ওই হোয়াটসঅ্যাপ গ্রুপে?
হ্যাঁ স্যার এসছে।
আচ্ছা, তাহলে তোমরা এই পেজে আমি তোমাকে যেটা বলছি, ইউ জাস্ট ডু আপ টু দিস স্টেপ। ওকে, ইউ স্টার্ট ফ্রম হিয়ার এ অ্যান্ড জাস্ট ইউ আপ টু দিস। এই পর্যন্ত তোমরা করো তো নিজের খাতায়, নোটটা পাঠিয়ে দিয়েছি অলরেডি। এটাকে একটু স্ট্রিং করলে হবে, মাইনাস। হ্যাঁ, তো মোটামুটি আছে। এই 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 স্টেপগুলো তোমরা করো তো নিজে করে, আমাকে বলবে হয়ে গেলে।
স্যার এই পেজটাই করতে বললেন তো?
হ্যাঁ
বলছি শুধু এই পেজটাই করতে বললেন না
হ্যাঁ হ্যাঁ
তারপর?
হ্যাঁ 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 হ্যাঁ
হ্যাঁ এটা আসছে। আচ্ছা।
আসছে তো?
হ্যাঁ
আচ্ছা
হ্যাঁ আসছে এটাই।
ওকে, দেখি অন্যরা কি বলবে।
হ্যাঁ স্যার এটাই আসছে।
অভিষেক কোথায়? অভিষেক
হ্যাঁ স্যার করছি। হয়েছে স্যার।
নো বিপ্লব, বিপ্লব আছো?
হ্যাঁ স্যার আছে স্যার, ওরকমই আসছে স্যার, ওখান থেকে ই এর ভ্যালুটা বসিয়ে আর কি।
আচ্ছা আচ্ছা ওকে, ঠিক আছে ওকে। Then you see, as I said in the green ink, that sum over R inner average DER. This is the kind of mechanical work done by the external agency to lift the systems of ensemble from energy ER to ER plus DR. Thus, minus sum over NR is the work done on the external agency with the system. Hence, minus 1 by eta, this one is the average work done by the system, right? So, work done by the system on the average. So, this is the work done. Then you see, if you compare this with the existing relation, thermodynamic relation, first law of thermodynamics, dq equals to du plus pdv, then you see this should be equals to beta times dq, right? dq is to du plus pdv. This is the work done, right? This is due internal energy, change in internal energy, and this is the work done, and that total is basically dq, the heat absorbed. So this is beta dq. Then dq is equals to 1 by beta of this one, 1 by beta d of this one, and you know dq is tds, right? And tds, and therefore you can write it as ds by k into beta. Beta is 1 by kt, and therefore you can write like this, and hence you can write beta times u minus a, this one, because you can write it as 1 by beta d of s by k, right? And therefore you can equate them, and then you can write beta u minus a is s by k. So maybe recall later for entropy calculation. Okay, let us keep it aside. Now you see, from this you can write that u minus a equals to beta. If you bring beta here, then this is 1 by t, so ts. So u minus a equals to ts, and therefore a equals to u minus ts. You see, now you identify this a as the Helmholtz free energy, and once you have the Helmholtz free energy, then you can calculate many things actually that we have said here. So basically the idea is that where is a, that this is the kind of partition function, and that is related. So you can once it is known to you, partition function, immediately you can write this expression, which is nothing but your Helmholtz free energy, and actually you define this one, and eventually you have concluded that A, or identified A, is nothing but Helmholtz free energy. Okay, so once you have identified A, this as Helmholtz free energy, that means there is a connection between free energy and the partition function, and then from free energy, you know, you can calculate everything, right? Every thermodynamical quantity. Now you see here, now we further go ahead. Well, this is yet another way of writing this. Once I have said this, then you can go through this. I cannot repeat another thing. There is no point of saying an alternative way of doing this. Now see, therefore A is minus kt ln the partition function, right? And therefore Qn, you know that Qn is sum over e to the minus beta er and sum over all states. Okay. Now you see, now you recall this A, that is the Helmholtz free energy, and A equals to U minus Ts, and again you know that from thermodynamic relation, du equals to T ds minus Q dV plus mu dn, right? And from here you see dA equals to du minus T ds minus S dt, and this U du is this. Okay, so you can put it back here. Then dA equals to du, you can put this one here, and then you are left these terms also you consider, and this and this cancels. You are left with S dt minus Q dV minus mu dn. Now you see, using this relation, you can calculate S as dA by dt provided V and N constant, right? These are 0. And A is known to you in terms of ln of Qn, and therefore you can write it in this form. Okay, this is one way of writing the S. Okay, this, and put A, and then eventually you can write it in this form. Similarly, P from here, then make this and this constant, and then dA dV. If you do dA dV with the minus sign and put T and N constant, and then you put A, then you can, you have to remember these things, okay? Or you have to calculate somewhere if you need to calculate pressure. Once you calculate the partition function, and eventually you have to utilize, or you have to use this relation to calculate the pressure in the system. Similarly, if you want to calculate the chemical potential, obviously this has to be 0, therefore T and V has to be constant, and dA minus, not minus, means dA by dN, and that can be written in terms of the partition function in this form. So these are the very key relations that you have to use to calculate the physical quantities, macroscopic quantities, using the partition function of the system. Okay, and U, I think I have already said you can write as minus del beta U of the partition function. This is one of very useful way of writing this U in terms of partition function. So U equals to minus del beta Q. And of course, this is same as this. We have already seen earlier also. This is a standard definition for average. And if you do this, then eventually you will find, you see from this, you get this. If you want to calculate the specific at constant volume, then du dt at constant volume and number of particles, and that can be written in this form. You just check all these things, okay? So that I have already checked. You check by yourself. Unless you do by yourself, just looking at this, doesn't make much sense. Okay, so given everything is given, I have tried to do things more explicit way, and also consult a Patricia and work out these steps. Okay, and CV is this. Now gives energy, these are the energies, and this is equals to mu n. You can check this one. Okay. Now again, you recall that P equals to KT. What is that P? KT del V of this. We recall this expression, okay? this, and then put the value of expression for Qn, and then do little bit of algebra mathematics, take the derivatives, then eventually we'll find this. From there we will get P equals to, I rewrite this here, this, and this will be minus between beta r del er del v, and this is Qn equals to minus PR. Now you see this is the PR, this PR, then del er del v, and PR is NR average by eta del E del v, and so P equals to minus 1 by eta sum over R NR average del ER, and this one, now you see, now if you take this dV this side, then P dV is minus 1 by eta, this, and this is what is your mechanical work done, right? And that actually turns out to be P dV. That also we are showing you explicitly. Okay, so that is what we said earlier, that that you have already calculated this portion. You see this portion is nothing but P dV. That is the mechanical work done. Now let's look at the entropy expression under the treatment of canonical ensemble. I think let me stop here because it will take a little bit of your patience here. So we will talk about it maybe in the next class. And so far, basically, what we have done, we have seen two approaches. One is the canonical. Of course, I mean we are talking about the canonical ensemble, and we have tried to figure out what is the probability of finding a system with some energy ER. For that, we have adopted two procedures. One is the system is in equilibrium with the reservoir, with a huge reservoir, and then we have looked at the distribution of energy, or distribution, actually the sharing of energy between these two. And in principle, actually not in principle, actually for canonical ensemble, the system macro state of the system will be defined in terms of temperature. That is one thing. And this canonical ensemble is superior compared to micro canonical ensemble because it is easy to maintain the equilibrium temperature rather than fixing the energy of a particular system with a little bit of energy. That's very difficult. That's very difficult to measure. That's difficult to maintain. And many times it is very difficult to actually calculate the total number of microsteps of a microcanonical ensemble. And therefore, it is easier to maintain the system as constant temperature, and that's why you assign the system with the macro state N, V, and T, constant temperature, and from that, you can go ahead and you can look at the energy sharing process, and you can find the probability that the system could be found with the energy E, and that we did assuming that the system is in equilibrium at constant temperature, equilibrium temperature. From there, from the distribution of energy, distribution of exchange of energy processes, you obtain the probability, and the denominator is basically termed as the partition function, which is sum over all states e to the power minus beta En. En is the nth step, and sum over n is the basically total number of possible steps, and that is what is called the partition function. And partition function is very important. You have seen that partition function could be related, connected to the Helmholtz free energy. In turn, the Helmholtz free energy is connected to all other physical quantities available. I have shown you the expressions that once you know the partition function, you can calculate all possible the Helmholtz free energy, and hence all possible physical quantities or thermodynamical quantities using those relations. This is one approach, and another approach is that consider an ensemble of systems. You have eta number of systems, similar kind of systems that you have. আচ্ছা, তোমাদের এরপরে কোনো ক্লাস নেই তো? যদি না থাকে আমি 2 মিনিট নেব জাস্ট টু কনক্লুড।
না স্যার নেই।
Okay, so another approach is you consider an ensemble, and there you try to figure out the possible sets and what is the number of possible and what is the number of modes or configuration corresponding to each set, and which set gives you the maximum possible configuration, and eventually that most probable configuration will correspond to the average value of the systems having the energy ER, and total number of systems is eta, and therefore take the ratio that will give you the probability that the system will be found at particular state ER, and that again turns out to be e to the power minus beta ER by sum over e to the power minus beta ER, and sum over e to the beta ER is basically the partition function. Again, same thing, we have used the partition function to calculate all thermodynamic quantities and given the relations, and with that, and also we have figured out that we assumed all these things are back calculation. Actually, we know that will happen. Okay, we have assumed exactly that in that manner, such that it actually is a free energy, Helmholtz free energy. So basically, it is like making people fool that let us assume A like this. Actually, we have assumed A like this, knowing that A will be the Helmholtz free energy. Okay, so I'm not making you fool, but this is the kind of approach that we adopt, that assume this, and if you play with this, and eventually it will turn out to be turn out to be the mechanical work, and therefore dq, and from there you eventually find that A is nothing but Helmholtz free energy. You identify A as Helmholtz free energy, and Helmholtz free energy is connected with other things in terms of other relations, thermodynamic relations, and therefore if you know this partition function, you can calculate many things, and that is the essence of the statistical mechanics. And we have also shown that this mechanical work that we physically told you, that mathematically we have shown, that is nothing but PdV, which is actually the mechanical work done, and therefore everything is in place. Okay, then you know that the entropy, if you are in the domain of microcanonical ensemble, you know what are the total number of microstates available, and then there is a relation S equals to K ln omega. That relation you obtain because of S is the additive quantity, and number of microstates are the multiplicative quantity. From that relation, you get a connection between entropy and the microstates, and that's the relation that you have in the microcanonical ensemble. But in case of canonical ensemble, you have yet another relation. You have yet another expression for entropy in terms of the probabilities PR. That we'll talk in the next class. Okay. Till then, you just go through the notes and do the calculations explicitly. ঠিক আছে অভিষেক?
হ্যাঁ স্যার।
ওকে, কোনো প্রশ্ন আছে?
না।
ওকে, গুড বাই।